afternoon, everybody. I welcome you to the plenary session, or the last plenary session of the day. It's about data cubes, advances, and applications. It will last about 1.5 hours. And I want to say a few other couple of things. After this last plenary session, there is in the rooms downstairs still activities ongoing until 7 o'clock. We have the BiDS'25 demos. There are the booth sessions and the birth of the feather. Also, on top of that, there is the conference dinner starting from 7 o'clock tonight in the House of the Black Hats, which is the most iconic building, I heard. And it's also possible, if you have not registered, to just turn up there, but very important is that you bring your badge. And I would like now to welcome on stage Felipe Carlos from IMPE, who came all the way from Brazil, to tell us more about satellite image time series for Earth observation data cubes. Welcome, Felipe.
It's already working? Okay. So thank you so much, Chair. And in this presentation, I will be presenting on behalf of my colleagues Gilberto Câmara, Felipe Souza, and Rolf Simões. And this presentation is about analysis of big Earth observation data cubes with satellite image time series. And our goal with this presentation is share with you our lessons learned and experiences, ideas, and concepts we are using to apply Earth observation data cubes to create land use and land cover maps. So to start, first I think it's what is an Earth observation data cube. So in our case, we define this as a multidimensional array where we have for each pixel the variation in time. And of course, pixels are aligned in space. And on top of that, in our definition of data cube, we also include a grid system. So this allows us to process data like on scale, terabytes of data, because when we build the data cube is already divided in multiple tiles. And when we are dealing with data cubes, the good thing about it is the possibility to access to image time series. So in a data cube, given one location, it is possible to extract the full variation of that same location over time. And of course, we can put this together with like labels. So we know one specific temporal behavior is related to agriculture, forest, pasture, and so on. And it's interesting to have this kind of variation, this kind of temporal information, because when we are dealing with land use and land cover classification, and in our case, we mainly work with Amazon, for example, we have regions where we have these seasonal or kind of objects that have different behaviors over time. So for example, in this image, in the left side, we have one region where we have a flooded area. And few months after, the same region have no water anymore. So this is why it's interesting to have this kind of time series information, because then we are able to use this information to detect or map this kind of objects. And with time series, as I mentioned before, this is possible. So this is to show a timeline of how a deforestation looks like. So we start with the forest, then we have one small period with a deforestation, and then after the deforestation, things change and evolve to pasture, for example, or any other type of temporary agriculture. And using time series, it is possible to map this kind of information. And based on these data cubes and time series, what we are doing to map and create land use and land cover maps is to use what we call time first, space later approach. So basically, in this approach, we use the time series to do the first step classification, so to detect what is like in the image, deforestation, water, agriculture, and so on. And after, we use some specific methods like smooth methods to consider the spatial context to enhance the final classification. So for example, when we use this method, we produce what we have in this left side, this unsmoothed classified map. So for each pixel we took the time series, put in a machine learning method, and this machine learning returned the class of that specific time series. And then, I don't know if it's possible to see, we have like a classification with a lot of salt and pepper effects. So we have like one block of forest, and in the middle of the forest, we have multiple classes of deforestation. This happens because in the time first, space later approach, we are doing classification pixel by pixel. And when we apply this space later, we basically do one kind of smoothing in the results. So we standardize like areas with the pixels in that specific region. So for example, for the forest, if we take a look in the right side, we see this Bayes smoothing, and the forests don't have like these salt and pepper effects anymore. So this is how we use this time first, space later approach. Classify using time series, and then fix and enhance the results using the spatial information. And to implement this approach and to handle data cubes, we are developing this SITS-R package. So this package was, we started developing it in R, so it's the main API in R, but a few months ago we launched this new version in Python as well. So the same features we have in R, it's also available in Python. And with SITS, all the steps required to do this land use and land cover using data cubes and time series are available and already implemented. So if we use SITS, we are able to first create data cubes. Then, using the time series from that data cube, we can create our training data set. So basically, in the training data set, we link for each time series we have one label. So we say, this time series, this temporal behavior is related to water or is related to agriculture, and so on. We also have quality analysis methods. So when we are building this training data set, we have these specialized methods to evaluate the training data sets, enhance, and then produce better results. As soon as we have these land use and land cover samples available, we can train machine learning models using it. And then, with the model trained, we can do the classification, apply the smoothing algorithms, as I mentioned, to produce the final land use and land cover map. And thanks to this stack availability, in SITS, it's possible to create data cubes from multiple sources. So for example, now, here's just a few examples. We support create data cubes from Digital Earth, using data from Digital Earth Africa, Amazon, Microsoft Planetary Computer, the Copernicus Data Space Ecosystem, Brazil Data Cube, Swiss Data Cube, Digital Earth Australia, and many more. So using this standardized interface, we are able to create cubes from these sources. And of course, during the operation itself, it's possible to combine cubes from these multiple sources. And as we are here sharing our experiences, one thing that is very important for us using this time first space later approach is the concept of objects and events. So objects, we say, is everything that exists, and events happen. So for example, here we have this volcano. It's an object because it's there, and the eruption is a kind of event for that specific object. And this sense of what are objects and events, it's important because when we are modeling time series to do the classification, we need to take care of these events to ensure and have good results. So one example is when we are dealing with deforestation. Deforestation is basically a sequence of events. So we start from the native forest, and we have different types of events like degradation by logging, degradation by fire, and then we have the clear cut, so when they remove the trees, for example. And using this idea of objects and events, when we are building the training data set, what we do is create training samples considering not only the temporal behavior of the objects like water and things like that. We consider the event itself. So how like a deforestation event looks like in the temporal domain. So here we have few examples of a work we developed. So we have as we have multiple types of deforestation, for example, starting with fire or the removal of trees, we have them listed here. So burned areas is one type of deforestation, and here is the signature, the temporal signature of this specific event. Same for cleared area. Forest is more stable because in this case is an object, and forest cut with regeneration, it's interesting because we see the forest as an object, and then we see the event happening in the time series. So you see we start with EVI and DVI like high, then we have a drop, and then start to regrow where people deforest these regions. So basically we use this approach, this idea of events, to build the training data sets we use to create our machine learning models. And when we apply this, we are able to produce good results. So this is one comparison. In the left, we have the results we are producing using SITs and using this time first, space later approach. And in the right side, we have this visual interpretation results. So nowadays, to detect deforestation, this visual interpretation is very high accurated. And when we do these event-based training samples, when we collect samples thinking about the event, we are able to detect the same polygons, like deforestation polygons, as the visual interpretation do. So it's like a very promising result, and we are using not only for deforestation, but also agriculture monitoring and other types of monitoring. And of course, this means if you want to have good results for land use and land cover classification, we need to have good training data. And when we are building these data sets, it's required to have like experts' knowledge, because when we are mapping, for example, what is the temporal behavior of a specific class or a specific event, this requires specialist knowledge. And here's just to show like few examples in the classes we detect and the spatial, temporal behavior of it. And in SIDS, to support this, like this process to collect this data set, we have specific methods for that. So for example, this is one self-organized map. So this is one way SIDS use to plot in a two-dimension figure the time series and the labels associated to each time series. So what is the idea here? The idea is time series with the same labels. So in this case, these are land use and land cover different labels. But the idea is same labels needs to be like together, because then they are similar. And this is the same for all classes. So this is one way we visualize and enhance the training data set we are building. So if we have a very like sparse result, then we need to improve the training data. And to finish my presentation, I would like just to mention a little bit about the model and the map evaluation. Because when we see many papers publishing results about these land use and land cover maps, people usually mention the k-fold results. This is what this figure is from a work we developed a few months ago, comparing convolutional and attention-based methods to create land use and land cover maps. And this is a very hard region in Brazil to map. And when we go collect samples and evaluate, considering only the k-fold, we have something like 98% of accuracy, which is very good, okay? But when we go and evaluate the map itself, not using only the k-fold, we have very different results. So we see, for example, for urban areas, for example, results that are not very good, same for temporary crops, and so on. So the main point here is to talk about the proper estimation accuracy method for land use and land cover maps. So this is one thing we are using, and this helps us a lot to enhance the training data sets and all the workflow we have. Because applying the proper methods to evaluate the maps we are creating, we are able to then understand if we need to collect more or less training samples and keep the workflow running to produce better and better results. And all these things I mentioned are already available and implemented in SITS. If you want to learn more, we have this online book where we present each feature we have with a specific use case, so it's possible to understand when and why to apply each method available in the package. And this is what I have to share. Thank you.
Thank you very much, Philippe. Do we have questions from the audience for Philippe? Okay, if there's no question for Philippe, we have one question for you. How do you see your SIDS software evolve in the context, for example, of less availability of the Google Earth Engine? How do you see your role and in that context?
Thank you. Yeah, so one of the things we always try to advocate is the use of open source software. So in this case of the Google Earth Engine, many institutions start to use Google Earth Engine because it's easy to use, the data is already there, so it's just create a script and start processing the data. So recently they announced these, they are start to put some prices to use the software, so you have a limitation to use Google Earth Engine, and above from that specific limitation you need to pay. So in our case in SIDS, we always try to keep things simple. So we have easiest possible software so people can just start using it. So this workflow, for example, I presented, starting from create a data cube and go to the classification. We only have 6 commands to do that. So 6 commands, 1 command to create the data cube, another command to extract time series associated to samples, another command to train the model, to do the classification, then to do the smoothing, and another one to do the mosaic, for example, to have the results in one chip. So it's basically the open source software, people can use it, and we advocate for that because then we avoid, and this is important for institutions, for example, when they start to implement, create some product, for example, it's important to have this long sustainability for the things they are developing.
Philippe, we have one more question from the audience.
Sure.
Thanks very much for the interesting package. Could you give us really shortly just maybe an impression of how much data, do you have some experience how big types of data, how many, I don't know, gigabytes, or how many scenes you be processing, and how long that would take or something like that?
Good. Yeah, so I can share one example we are developing now in Brazil. So we are basically creating land use and land cover maps for the whole Brazil for the whole Landsat collection. So far we processed 25 years of data, Landsat data. This means something around 50 terabytes of data, and the software behaves normal. The thing is that we need to have machines for that. So in our case, we have a proper cluster, and the software is able to run in that cluster, distributed in multiple nodes and all these. So yeah, is one example. And just to mention what we are mapping using SIDS, the full Cerrado biome, which is huge, same for Amazon itself and the whole country. So we have different projects using, and Sentinel data as well.
So we thank again, Philippe.
Good, thank you.
So the next speaker is Evelyn Nuema from University of Tartu, and she will present on developing a data cube for biodiversity and carbon dynamics assessments in Estonia with remote sensing. Evelyn, the floor is yours.
Thanks. So I will present another data cube. Just the previous talk was nice, maybe intro already into data cubes, and was example on how data cubes can be used on land cover mapping. So I will show a different use case of data cubes. And before I show how we did it, I start with why we did it. So what is the problem that we try to solve with another data cubes, data cubes, there are a lot of data cubes. So the initial problem, actually, what we're trying to solve is that we can't measure everything everywhere. And I'm talking about here actual physical processes, that if you measure soil moisture, greenhouse gases, mapping biodiversity, that is very heavy work that you have to go out and actually get the ground measurements. So we have maybe some points, like here, for example, Estonia, 1,000 points of soil samples, but we would want to know also beyond those points. So we would want to know what is also everywhere else, for example, soil organic carbon. So ideally, we would want to see full-scale map. And here now comes into play remote sensing that potentially could help, and data cubes. And what is the, so unlike land cover mapping, it's a little bit different task. It's a classification task. So here we are actually modeling we try to model some processes actually. And how we in generally do it, it's a spatial modeling. What we are trying to do is spatial modeling of carbon emissions and storage and biodiversity. It's a very ambitious task. We have a big consortium to do it, but basically it starts with fieldwork that maps this on the ground. Then we have the points on the landscape. And all those processes can be somehow explained with some environmental covariates, that climate, like temperature, moisture, something, and usually those can be somehow measured from remote sensing, or at least there are some proxies to that. And there, ideally, they would be somehow everything available, which brings to the data cube that the data has to be somehow in a unified form, easily available, that we can align, like sort of work with the ground measurements, and then all those covariates that we could do spatial modeling. Another take, what we took it further is that, or maybe we took a step back, because, I mean, you see also here in the conference, we have all those amazing tools. I would say that we have everything here. We have a big amount of data, we have all sorts of scripts, we have X-array, we have embeddings, and we can chuck everything into machine learning model and into high performance computer, and then it spits something out. Maybe we don't know what it is, but it does something and maybe predicts something. The problem here is that with this kind of processes, what we want to model is that the moment you show it to the domain expert, they would shut you off, because they will stop talking to you because they need to understand what it did. And maybe for a reason. And you can't also tell them that, you know, here are the scripts, just do it. Usually it's beyond their knowledge. They are not computer scientists, and we can't expect that they are computer scientists. So usually it's, in my experience, it's not just simply enough. Here, take the package, run Jupyter Notebook, and then it's done. So what we, as we have several teams with whom we are working with actual soil scientists, greenhouse gas measurement like who measure greenhouse gases, also botanists, then we realized that we have to make it very easily available, and also to be able to them to show what the data actually is, in order that they would trust to give us actually the ground measurements that they have collected over 10 years and still collecting, to ground validate and to put into the models. So how we did it, it's still work in the process. It's a really big team effort. It's a two years project already. So basically, the data cube, we are talking right now about 3 main components that we are developing in the in this concept. So first is the data preparation, which is heavily on us. We are geoinformatics team. Then the other thing is the data cube itself, but then very important part for us was also the how to access the data and metadata. But what is the data? Usually we tend to forget it because it's quite an annoying thing to do. Nobody wants to do it anymore once the data is there. And then also exactly what we put a lot of effort in is the data viewing, that you can actually see all the covariates. It's not some X-array or something, which is also good, but here we are sort of trying to make it very simple. And starting from data preparation, very quick overview how it is, like the processing part, we developed it for Estonia, because we are right now only working for Estonia. We still had it to divide it into some zones, because Estonia is small, but still big enough not to fit everything into one computer. And then the main foundational decision was also that we divided, we made like a reference grid, which was the base that everything has to align with the same reference grid, 10-meter resolution, and then the basic assumption was, of course, that we use Estonian National Coordinate Reference System. So this was the base assumption where everything started. Then for the data preparation, we used Sentinel-1 and Sentinel-2 images. And yes, we used Google Earth Engine with Python API. When we started, then Copernicus data spaces were not there. So that was, of course, the easiest choice to go. Everything else we use open source, but that was the only thing that then was available. And now we are actually looking into ways how to transfer all our workflows to Copernicus data spaces. But right now, everything was done there. So we calculated, basically what we created was composite images of three seasons for all the years that the data is available, and several, like the bands, and then all the vegetation, 14 different vegetation indices, and the median, mean, max, and standard deviations. Then in addition to this, which usually doesn't come maybe as data from space, but from airborne, is LiDAR data. That is everywhere kind of available, but the processing, again, is super hard. But we know that for biodiversity, it's quite important, let's say, like information that can complement very well the satellite imagery. So we spent 1 year in actually pre-processing the point cloud. Estonia is fully covered every 4 years, again, like fully. What we, of course, like a side note there is that most countries get the LiDAR data from land boards, and the purpose of land boards to use the LiDAR data is different than we need it. What land board needs is only ground and then the uppermost reflection, like the bounce, so they need only 2 things. And everything else in between, they don't really care. So they usually put them something into unclassified or something, but that's everything else in between is what we care actually, because we want to know the vegetation structure. So we had to spend 1 year to reclassify the LiDAR points before we could start calculating the indices, actually what we needed. And this we did mostly with PDAL and using X-array, and some post-processing in both was actually in GDAL. And for storage, we used Google Cloud Storage because it's connected to GE. Obviously, that was the easiest, but then we moved everything to our university's high-performance center. We used it also for some processing, actually. So basically, we created like a lot of full-scale Estonia composites for further modeling. Then the second part is how the data can be accessed, is that all the data was then indexed in the spatial temporal asset catalog as stack. So there it's also basically available. Another story is that how to structure stack. I heard also from the workshops interesting discussions. You don't want to know how many times we reorganized it and how many times we reconceptualized how we name our files. Thank you here for our team member Holger, who worked a lot in that. But basically, it's very important to start immediately thinking of that, because if you get so big, then the structure starts to matter, and you have to really rethink. It is also available in QGIS, basically for QGIS Stack API browser plugin. It's not very comfortable to work with, but for very simple GIS users, it can do the trick. The problem there is that you don't see really the data so well immediately before adding it to QGIS. And then the other side also for data access is, of course, metadata, where we use GeoNetwork. And let's say that the GeoNetwork we use there also to comply with the ISO geographic metadata standards. We put quite a lot of effort into really properly describe all the indices and what are the min-max values, no data, everything that usually tends to be discarded. Like nobody wants to write that. And then the last component where you actually, so those were still quite technical, because DataCube usually is quite abstract for most people. It's something somewhere in the cloud and you can access it with some complicated scripts. And then exactly when you show it to the domain specialist, then they're already like, I can't run those scripts. Can I just see the data? And to actually see if it makes sense in the concept of these processes or something like this. So we developed like a DataCube viewer, which is basically just a web page or geoportal that can that shows all those layers can be visualized. and they can actually then see everything. And there we used also basically an Elixir language with Phoenix framework. That was just why we chose it, was basically because we don't also have like front-end developers and back-end, and that was just a simple way around it. And MapLibre instead of Leaflet, because it has pretty cool new features, like for example this 3D globe, and it's very it's faster in performance when you work with different data types or sources. And also GeoServer was behind it, actually. So everybody can, you can scan the QR code, then you can see not all the data is yet publicly in the data cube viewer, because putting it there takes also time, but most of the indices are there. And yeah, basically it allows very simple, like everybody can do it, just click the layers. You can also check the values in one specific point. The further development basically would be that also take some zonal statistics areas and also extract the values immediately that you load points in and take the values from the data cube without some complicated scripts. But we have also basically the scripts available that you can use and then extract also with those if you want to. So thanks first of all to all my team who has worked really hard on this, and the work is still ongoing. And if you want to know more, then we have also booth down in the exhibition area, so feel free to step by and ask questions.
Okay, thank you, Evelyn. You stayed well in time. Interesting talk. Are there any questions from the audience? Yeah, there's one over there.
Thank you very much for a very nice presentation and also sharing your experience end-to-end. So it's not only creating the data cube, also making it available, accessible to others, and I think you showed a very nice example. My question is, you mentioned while working with GeoNetwork, you need to enter all the metadata. Mm-hmm. Probably you had to do it also for the stack catalog and probably for other components, I believe.
Yeah.
So
okay.
My question is, how was your experience regarding to that? You need to repeat that work again and again for each component, or is there a way to make them interoperable somehow?
Very good question. So actually we didn't sort of repeat the work. Well, the metadata is in both, but the stack catalog only has this basic information extent and coordinate reference system and those things. But those we extracted actually automatically using Rasterio package. So this can be done automatically. Basically, this work was almost automated, that it reads into the stack. GeoNetwork, however, this is manual work, and it is quite a lot of effort, but this was the decision that we made in the beginning, that exactly if you put so much effort in already making this data sort of very easy, then without metadata it's kind of useless. But there's also ways how to a little bit automate this, because you can, if you create one index already, then you copy the template, and a lot of information is repeating, but it is, yeah, effort. Metadata is painful.
I think that might be also interested to include in the stack catalog, because it might become the primary main to access the data, and in that case, all these detailed metadata might be useful.
Yeah, I forgot to mention that, for example, from the viewer, I guess we see that the most people access it from the viewer. So from the viewer, in each of the layers actually has this information point, information like a button, that leads actually to the GeoNetwork metadata, and from the GeoNetwork metadata, you only can get the stack link. So the access actually goes like, so we don't give people the stack, because stack is also, for most people, actually still quite complicated to use, if you're not like from geospatial world. So basically we assume, yeah, this sort of access.
Thank you.
I would also have a question, Evelyn. So your group is a strong advocate of DGGS, right? We saw Alexander's talk earlier, was great.
Yeah.
So we did notice there was no DGGS used in this study.
Not
so
yet.
First question,
Not yet.
Would you like to use it, and what are the obstacles for using it?
So the next steps would be actually the same data cube. We are right now working on this, that it goes to DGS. That's why we also chose the MapLibre and show 3D globe and everything like this. So many decisions were already made in that direction, that we actually right now starting to move that it will be in DGS. Yep. Next conference, we can show it in DGS.
Excellent, we hope so. 2 years, BiDS'25. Yeah. Great, I think we would have time for one short question if there's one more. No, otherwise, thanks again, Evelyn.
So I would like to call the next speaker to the stage, Athanasios Trantas. And it's also a talk in the area of biodiversity. So we get presented BioCube, a multimodal data set for biodiversity research. Yes. Welcome.
Hello, good afternoon. Okay, I use this, huh? Okay, yeah. Hello, good afternoon, everyone. I'm Thanasis. I work for the Dutch Organization of Applied Scientific Research, short name TNO. On the group Intelligent Cyber Physical System Engineering. I'm here to present BioCube, a work we start doing one and a half year ago, and finally we're able to deliver something. This is a byproduct of a Horizon European project called BiDS'25. The team mainly work was done by Stylianos, our ex-colleague now. He did his internship with us, Martino, Elena, and me. So I'm gonna, the agenda is pretty short today. We have only 15 minutes. Short introduction, how we engineered BioCube and some next steps. As I told you, the main partners are BiDS'25, TNO, and we use also the Dutch supercomputer center called SURF. But why biodiversity? I really like to show this image when I talk. A lot of people think that recession, climate change are big problems, but in practice, biodiversity collapse is the biggest of all. And without biodiversity, we cannot sustain life on Earth. We put a lot of pressure to it, and yeah, we inflict changes that sometimes we don't want to. And it has a lot of impact on how Earth can sustain life and sustain us also as human race. So trying to solve challenges and problems in biodiversity, I think it's one of the most core pillars we should look into. So when we want to model my biodiversity, the previous speaker gave a nice introduction, but it has 3 layers mainly, above surface, and below surface. And when we look to model it holistically, we lack these 3 layers, at least on a single place. So modalities. We seen the past days also through the hackathons that there's a lot of modalities available. The modality is like a different encoding or representation of data, of signals. For biodiversity, the most common modalities are, of course, images, audio recordings, genomic data and their taxonomies, environmental DNA, called eDNA in short, satellite and remote sensing data, big data from space, of course, geospatial data with different GIS, ArcGIS layers, climate data, textual data, and of course sensor data that we can get from ground stations. So for us to build BioCube, we took data from all these sources. Not an easy task, because again, we need to cover all these layers, right? And as I told you, there is not a single source that contains all of them. So we have to go through at least 10 to 12 different providers and get data. So for species data, what we have done, we have images of species, audio of these species, descriptions. This is a lion, for example, from this taxonomy, from this family, their eDNA, their distribution, some elements that show if this species is under extinction or so, their taxonomy, the phylum, the class, the order, the family, the genus, timestamps, latitude and longitude where the species observation is recorded. For the surface now, we take data from ERA 5. For the surface, we use 4 main components the 10-meter U component wind, the V1, 2-meter temperature, mean sea level pressure, and we also got some other features called geopotential, land, sea mass, and soil type. Of course, way more pressure levels. We went to, I think, 13 different levels. Most of, actually everything that existed on Era 5, we just grab it. Also some indicators. We got indicators for land, for forest, and agriculture. This is in percentage of the land. Of course, in DVI, which is an indicator for the greenness of the biomass. Red list index, as I mentioned before, it's a very strong indicator of changing the state of global biodiversity. But yeah, some challenges we faced and why that led us to create BioCube in the first place. Biodiversity data are not easy to work with. As I mentioned before again, dispersed and fragmented between different resources. Lack of protocols. There is not a standardized collection method or protocol. Everyone does whatever they like. The quality is varying, and most of the data set do not come with validation metrics. The size and the storing of them starts from megabytes, from simple tiles, simple files, and you can end up with terabytes of data. Sampling frequencies. This is a very critical one. You can have data from hourly resolution to daily resolution to monthly, and worst case scenario, you're going to get indicators with yearly resolutions. So not so much information here. Of course, as we've seen, multiple modalities that we require in ecology in general, but also in biodiversity. And how these data are being handled, either pro or post-processing, they are different. And the final one, which, it was interesting also for me to find it out, was different geodetic grounding systems. So today, a few presentations, I think I already counted 5 different geodetic systems used. So big challenge also this one. So we need to engineer a data set for a multimodal data set for biodiversity, so researchers like us and others can do research in a more compact way, in a more easy way. So why? Yes, of course, to solve some of the previous mentioned challenges. The goal is to create a unified data set, scalable for multimodal data, flexible also, integration of spatial but also temporal features. The first speaker gave a very nice overview of what is a definition of a data cube. That's why we call it also cube, because we are both spatial but also temporal. Looking also the time, I'm going to talk about this. So these are some of the sources we used, either through API or file-based, because some of them, they do not come with an API. So you have to do all this manual labor of going there, download the file, select the date, select even the whole file, because they don't come with metadata. Some of them are API-based, some of them are file-based. The challenge is that some of them, like the World Bank and the Red List, they give only the name of the country, so no coordinates, no nothing. So we get like bounding boxes for our data. Some limitations we hit also with APIs is like, if you start spawning a lot of calls, the system breaks, you get blocked for some time. The downloading time, of course, for Era 5, it's terabytes. The species name requests, so some sites have different namings, so this is a problem on ecologists. So they even have differences between how they call the species. There's not like a unified name. There is for most of them, but there are species that have multiple names. So our pipeline, how does it look like? It retrieves on the first stage the data. So it reads the files, either in a CSV format, NetCDF format, JSON format, right? As mentioned before again, these data do not come in a single format. So we created a pipeline or a workflow that can read from multiple file formats. fetches the data, retrieves the metadata from any kind of file we can find based on these providers. Then we go to the step number 2 where we process the data, we extract the relevant features, we round any kind of coordinates that are snapped or so, and we process any kind of images, audio. For example, in birds you have audios that you can hear it. There is a recording, for example, for 5 minutes, but the sound is only for a few seconds in the middle of the file. So we don't want to store the whole file, right? We want to hear only the bird singing in this specific moment, cut everything out. So a lot of pre-processing on this happen on the back end. Storage, in the end, we store in structured directories based on region, species, and data modality. So we have a folder per modality, species-specific subfolders, so each species contains its own image, audio, and metadata. This is the main concept, how it looks like. For the species dataset, because this is an extra dataset we build, again, there is a pipeline to create it. I'm not gonna go through it. It looks like a bit of complex. It is not in practice. We just acquire the data through GBIF most of the times. But some other times when we have, for example, images or audios for a species, we need to get the name of the species, then look for the species and get the data that exists in that location and then try to merge that with the rest of the spatial tiles. We created data frame with this data in a Parquet format. And we serialize the data to be compatible for this one, so we save them. A challenge we faced when doing that was that we cannot load all the folders, right? So we have like a terabytes of storage. We cannot load everything to create our species data set. We have to load in chunks, even in a high-performance computer with 4 terabytes of RAM. There was a lot of engineering happening to do that. But then we went a step ahead, okay? So we have a data set now. We have some files. We can read them, we can load them. How are we gonna use them? How the end user wants to use this kind of data. So 2 different methods here. So Fusion, a lot of speakers talked about Fusion. Data batch creation, which is a late Fusion, and the input to any kind of machine learning pipeline, which is an early Fusion. Looking at the time, I'm gonna go a bit faster. So the data batch, how it looks like, is a unified and structured data representation that essentially integrates all these multiple modalities we have in our data set. And it is defined by latitude, longitude, and a time step. By creating this data batch, we ensure that all modalities are aligned to a consistent framework, and any kind of modality can be independently initialized, so we can slice out of it. How it looks like in practice, we also use the and transform everything to WGS84 geodetic system. So you can think of BioCube as a data hypercube, and from this data hypercube, which has global resolution, we take a data batch, which is a slice at a specific time for the whole world. And if you sample a single data point from that, this data point contains your modalities. The sampling of our data so that it can be harmonized is on 0.25 degrees, which, correct me if I'm wrong, is 27 kilometers, 30. So each data point looks like this. So here you can see a visualization of different modalities if we plot them. So it's like a big tensor in practice with slices, where you can sample each of these variables however you like. Some statistics, I will go very fast through them. For the whole world, for 20 years of data, to create 13,000 batches for 20 years, the storage is 958 terabytes. Because someone asked about like how big are the data. Yeah, they are big. Some challenges and limitations. We have none and missing values. We focus mainly on terrestrial biodiversity in this data set. We do not take into consideration any kind of marine life. Saving and handling a lot of terabytes of data. Of course, data set pre-processing and creation takes days. We scale it up with a high-performance computer. For now, we limit our processing to Europe only, so we take a slice out of this cube. Yeah, and we end up with some source limitations. So, what you can do with BioCube, right? Now we have it, it's there, it's real. Ecologists, in general, anyone can do a lot of stuff. First of all, biodiversity modeling, you can use it to model biodiversity. Any kind of downstream ecological processing can be modeled, of course. Species distribution modeling, habitat assessment, weather and climate modeling. But why we built it in the first place, I haven't shared it. We build it because we need to train large-scale foundation models and fine-tune them. So our use case, our first use case is bioanalyst, the first foundation model for biodiversity. This model, yeah, is super useful for biodiversity dynamics modeling, at least that's what we have done. Species distribution forecasting, absence detection of species and monthly climate linear probing. Also, bioanalysis is real, it exists if you didn't know about it. And you can scan, you can find both our code bases and our weights openly available. We spend a lot of time and a lot of resources to make them fully open sourced, in contrast with other companies, mainly private companies, where they just share the model. They don't share how they train the model, how they pre-process the data, how they end up to all these fancy things they put in the papers. We actually open sourced everything. Yeah, and with this one, I will close my presentation. Thank you so much, and I'm available for any kind of questions.
Thank you, Athanasios. Do we have a question from the audience? In this case, I have one for you, Athanasios. It's a bit of, as well, interest from myself. Yes. You know the Destination Earth initiative. Yes. We have climate projections for the future, and I was wondering what it means for you, if you had a look at those projections already, and if you have plans to use them, because looking in the future for biodiversity might be quite interesting.
Yes, yes. We haven't looked them, and there is the plan to look them. There is the plan. They are very useful. I was a colleague of mine brought them to my attention when we were designing BioCube, and that was a byproduct of the BiDS' project. Yeah, we weren't aware of that. So yeah, we strive like, okay, we need to build a foundation model or any kind of machine learning model with modalities, right? And we don't have any. We have some forecasts, but the idea with some of our ecologist colleagues, at least on BiDS', they said like, you can use pre-processed data, right? Estimates that can come up from different models, but these are giving bias to your underlying modeling process, right? So we went ahead to, that's the main reason we built it, to have as much as raw data as possible from the resources available, of course, right? So yeah, that's in general, but integrating more features to BioCube in the future, and because the current data set spans from 2000 to 2020, so it's not up to date to the latest one, and that's one of the, that's a problem from the data providers, right? So they don't give up to date, they don't update their data sources frequently, and there is not a way to solve that per se, because I cannot give them a call update like 2025 data, right? Even, for example, on Copernicus, we have NDVI till 2024, right? We don't have it for 2025. Yes, but I want to have like near real-time processing, how I'm gonna do that. So we need to work on these kind of things coming in the future. And this conference, I met like super intelligent people with great ideas, super eager to solve them. So pretty happy.
Thank you very much,
Thank
Athanasios. In Destiny, the projections goes up to 2050. So there's a lot of data to look
Yes,
at, so
yes,
it might
yes.
be interesting. Then we thank again Athanasis.
Thank you.
Okay, the next speaker is Yogesh Singh from Brockman Consult, and he will speak on Xcube and the Python data science ecosystem.
Hello everyone. So I'm Yogesh Kumar, and today I'll be presenting about the Xcube and the Python ecosystem, which provides federated access, interoperability, and dissemination. So kind of an end-to-end ecosystem that helps you for helping you with your big Earth observation data. A quick intro about us. So Brockman Consult, we are an SME located in Hamburg, Germany. We develop open source software for exploitation of Earth observation data, and we also provide consultancy and geoinformation services to public and private customers, and we mostly also work with a diverse base of space agencies and European institutions. A quick outline about the presentation. So I'm going to talk about the beginning of Xcube, the purpose, why it was developed, an overview of Xcube system, so what encompasses it, the data stores, a quick talk about a multi-data store, Xcube server and viewer, the resampling capabilities, GeoDB, finally the new versions, new developments like XC Engine, and how we use that in ESA Earth code. So I'm going to talk about integration. All right, so the beginning and purpose of Xcube was that this was designed, I think, almost 6 years ago, and the desire was to tackle environmental questions with conveniently accessible data. We have a lot of big data lying around, and it was not quite easy to bring it into a certain format which can be reused and be disseminated in a proper format. So we want to facilitate also visualization and sharing of this process data to different people, and we want to make sure that this process data is now available for communication for people. The purpose, so just in the few talks before, you might have heard how difficult it is for most of the people to access data from different sources. So Xcube ecosystem tries to tackle some part of it. So wherever we have APIs, we try to provide data stores. So that's first part is that we provide this convenient access to as many big gridded spatiotemporal data sources as possible. And the key part is that we mentioned big gridded spatiotemporal, not Earth observation data. That means every gridded data that's available can be provided via Xcube if there's an API and someone or us write a plugin for it. So for example, ERA5 is a gridded data, and something coming directly from space like CLMS is Earth observation data. So we also create analysis-ready data cubes from these sources. So Xcube allows us to do that. And we also provide lots of tools to exploit this data in a certain way. For example, you can resample your data from one grid to another. And this also makes sure that everything is in the same ecosystem. You don't have to install some of the libraries. You can do all of these things from the same ecosystem. You can also serve your data through OGC APIs, through stack catalogs, and since all the data cubes that we create are ZAR, it's quite efficient in storage. Then you can also visualize and disseminate and analyze the served data through the Xcube viewer that we provide. And finally, just want to tell that Xcube is built on the Spangeo data stack using Xarray, Dask, and ZAR. To also keep in mind that the community loves the Spangeo ecosystem. A quick overview of the Xcube ecosystem is that we provide this end-to-end approach from data access to dissemination. So 3 main pillars. The one at the bottom is the Xcube data stores, so where you can access data from varied different sources. To name a few, for example, CDS, CCI, CMEMS, EOPF, that was a new recent one, and so on. And then you have APIs through which you can do lots of processing. You have resampling capabilities, you have time series, you can create histograms and something like that. And the final one is the dissemination part, so the Xcube viewer and the server, which you see at the complete top. So as it says, it's a seamless integration with the Pangeo, so there's no lock-in, it's fully compatible, and it's an open source tool that you can, of course, contribute to or just use as you like. A quick intro about Xcube data stores. So as I talked, we have data stores for EOPF, CCI, CDS, newly developed Stack, Sentinel Hub, CLMS, Zenodo, CMEMS, soil moisture, ocean salinity, and a few more. Not all of them are mentioned here. And we also provide data stores for file system access, because not all of the data is available via APIs. Some of the data might be hosted on S3 or Azure or even file storage. So you can use the data stores to access data in a similar way. So your API access is always going to look the same. It's just the store object is going to change. You can always add your own plugins. It's a bit easier to do. And below there's an image which shows some of the available data stores, which is just listed above. And on the right, you see how we can create a data store. So you use the new data store function from the Xcube's library. You specify the store ID. For example, we need the stack from CDSE in an analysis-ready data cube format. So that's stack CDSE ARDC. And then you pass in your credentials. And that's it. And then you just do .open data. You provide the data ID, your specific parameters, your time range, bounding box, your specific spatial resolution, and your CRS and whatnot. And there you have it. Everything is lazy. So most of the things are lazy. And something that cannot be lazily loaded, you can preload them in the Xcube ecosystem. Now let's talk about the multi-source data store. So this also tackles the problem that most users want to create a data cube from several different data sources, and this can be done using this multi-source data store. So this was developed within the ESA's EOLinks project. It's more about the carbon science community. And it combines all the available data stores. So everything that's available, you can use it in here. It's easily extensible to add new stores. So as I mentioned in one of the previous slides. And you can bring all of your final data cube into a single spatial resampled source. So documentation is available over there. And on the right, you see how the concept works. So you have the Xcube in between, which has the several data stores. And you create cubes out of it. And finally, when you pre-process them, the output that you get is they are spatially and temporally aligned if the dimensions match for each of the cubes that you have requested. How do you do that? For example, you can do it by either configuration of a YAML file, or you can create a Python dictionary. So some of the properties over here are data sets. So you specify which data sets you need. For example, biomass from Zenodo, or CCI, the biomass data from there. You can also provide the capability to preload the data sets. So what do I mean by that is some data sets, they cannot be lazily loaded because they might want you to queue, wait for your download to get ready, and then they will provide you with a download link, and then the download link is a zip file. Now you need to extract the zip file, and then you have your data. So all of this is kind of taken care by the preload method from Xcube. It's available in CLMS and Zenodo. Then there's this data stores, which specify which is the data store that you're going to use from Xcube. Then you say the grid mappings, so which is the grid mappings you want your data set to be in. So the final one, the target grid mapping. And there are some general configurations as well that you can use. How does it look like in a Jupyter notebook? It's a one-liner command. So you import the multi-source data store, and you just pass in your config.yaml. And when you run it, you get a beautiful table showing the status of each of the cubes that you have requested. And at the bottom, you can see the global version of what I wanted in one of my config files, which was in the EOLinks project. And you can see the output below, for example, the two variables over there. And using this config, it's quite good because it makes your data set pipeline kind of reproducible. So if you just give this YAML file to anyone, they can run the same command and they will have the same cube by themselves. And as it says, no advanced programming skill required, you just need to know what exactly to put in the configuration file, and we also provide means to do that. Coming to Xcube server and viewer, the server is OGC Web Map Tile Service compliant, so it can be plugged into, for example, QGIS to provide you an API to the datasets that are now hosted by Xcube server. You have capabilities like time series, statistics, and other functionalities, as you can see on the right. So that's the viewer. And on the complete right, you see there are some statistics for some data points which are highlighted. So you might be seeing a circle on England, somewhere near Latvia. So those are the histograms for that, which are kind of color-coded, so you can match them. And then there's a slider. You can slide between two different variables and see the differences. So both server and viewer, they can be started from Jupyter notebooks. What's new is that we also provide server-side UI contributions. So that means the viewer is not just limited to what we provide. You can add your own charts. You can add your own maps. That's available via the material UI library. As you see on the right, we can add like a histogram. Over there, you can have some drop-downs that you want to choose some variables. So you choose that area, and now you want to compare two variables from this data cube as a histogram. So you can do this via Python, and it's available now in this viewer for you. Coming to the Xcube resampling, this is also a library that Xcube has, which allows transforming datasets into spatial grid mappings. It has three features. So the first one is affine read resampling, which means you're in the same CRS zone, so you just want to move from a higher to lower or lower to higher resolution. Then there's reprojection, where you want to go from different coordinate systems, so one coordinate system to another coordinate system. And finally, there's rectification, where you want to go from an unequally spaced grids to equally spaced grids in the provided CRS. So on the right, you see an example of Europe in one grid mapping, and then when you run this through this library, it maps it out into a different grid mapping that you requested. And if you are not sure which of the mappings is that you need, you don't have to do that, because Xcube resampling takes care of that. All you need to do is just provide the data set and the target grid mapping where you want to be it in. Xcube also has GeoDB, which is a geospatial database specifically developed for vector data. It offers an API which allows you to store, fetch, manipulate, share, and a few other things with the vector data. It's stored in geo-referenced database. And as I said, there's also this visualization and publication possible using this web services, and we have user management in it, and we also provide a Python API. Some examples of Xcube, where it is currently used. So it's used in Cyano Alert, EuroDataCube, the Agricultural Virtual Lab, and DPSTL platform, which you kind of also used as an integrated platform in the ESA Earth Code. XC Engine, so this is a new development. OGC EO application packages. So if some of you were in the demo, you might have seen what this actually do. So an application package quickly is a Docker container and a common workflow language file. So that the common workflow language defines what is the process that you need to run, what's the input, what's the output, which is reference to the Docker image. And how do you usually do that without the XC engine is that you have your notebook, which contains the whole processing pipeline. What do? So you have to turn it into a runnable script, process CLI commands, read data, write output, define a container image, write the CWL, test and debug until it works. So some people might not consider this as fun. That's where XC tool comes in from XC engine, and you just provide your Jupyter notebook and your environment.yaml. XE tool takes that and gives you a Docker image and a CWL file. And inside the Docker image, you not only have your application package, but you also have your server and a viewer through which you can visualize the output that is created from this application package. Finally, ESA Earth Code integration. So for those who do not know what Earth Code is, it stands for Earth Science Collaborative Open Development Environment. It's an initiative by ESA to empower researchers and scientists in Earth system science with fair tools and infrastructure, which is sponsored by ESA. And yes, so on the right, you see how that works. So you are at the bottom left. So you're a researcher, you need some access to integrated platform like DPSTL. That's where Xcube ecosystem is also present. And you have NORs, so Network of Resources requests from ESA, you get some compute, and then you do your experiments, you log your experiments to Open Science Catalog so that everyone else who are there can view your workflow, run your experiments. And there's a discourse forum, so you can meet with the community and you talk to them to discuss your problems. And finally, there's also going to be support for ESA PRR, which stands for Project Result Repository, which contains most important projects results which have come through the Earth Code platform. And it's mainly, who is it for, which shows at the bottom right. It's for ESA-funded science projects, for ESA scientists and developer, and also for platform providers like DPSTL. Finally, we have DeepCode, this tool which is provided, which was built also in the Xcube team for this Earth Code project, which allows users to publish their experiments and workflows to this Open Science Catalog quite easily. It's just a simple CLI command, simple for you, so you have to run it, and then it takes care of all the heavy lifting to do all the work to publish your workflow basically to the Earth Code. So that's it, and yeah, if you have any questions, please let me know. Please do visit us at the poster session tomorrow. All right, thank you.
Thank you very much. Are there questions in the audience? I would have one in the meantime for you. So Xcube is fully open source. Are there contributors outside of Brockman contributing to the source code?
Sometimes there are issues that people would like, or like some new features that they would like. So they're not really contributors, but they ask us to implement them, and when we have time, we do that.
Yeah. Are you open to additional contributors?
Yes, of course.
Yes.
All the time.
Yogesh, I have also one question to you. There's the OGC GeoDataCube specification, and I just wondered how aligned you are with your implementation.
Yes, so most of the data cubes that we generate, they have the attributes which are aligned with the OGC API constraints. So we try to make sure that all the data cubes have that.
Thank you.
Yep.
Right. Thanks again, Yogesh.
Thank you.
I would like to ask Dirk Tiede to come onto stage. He will present us interpretable single-layer representation of multi-temporal vegetation change dynamic for Sentinel-2 time series. Long title.
Thank you very much. Yeah, the title more or less explains everything, but I will show some videos to make it a bit easier to understand. Okay, it's not my work alone. We are from the University of Salzburg and also our spin-off Spatial Services. What we want to show is an application of data cubes. In our case, it's a semantic EO data cube which we developed over the last years, also presented at other ESA BiDS occasions. We propose here one application, a change detection and monitoring system that enriches base maps, so to say, with multi-temporal information. We integrate all Sentinel-2 observations, since Sentinel-2 is in orbit, based on vegetation dynamics. We want to show where things changed, when and how, and we make it accessible over the GTIF platform for Austria, but also as a dynamic WMS base map for different users to have a multi-temporal information base map instead of static, outdated ones. That is seamlessly linked with our Austrian semantic EO data cube. What is the semantic EO data cube? I just shortly want to show you this. In our data cube, the difference to all the others is every single pixel is labeled. It has a semantic information. We do that fully automated based on a physical model. That's SIAM in our case, satellite image automated mapper. No parameters are required, no training samples. It's fast. You can parallelize that worldwide, also between different sensors, as long as they are at least top of atmosphere corrected, which is very important. You can read that up. There is a link to the paper of that implementation. We use every data set in here, and then we just count, for example, the spectral categories. So it looks like this. Besides the spectral, the reflectance data we have for each pixel, if you imagine these are single pixels, different categories. You see we have also included all the layers which are cloud covered. If they have 99% cloud, maybe 1% is a valid pixel we can enrich in our statistical analysis. Because if we now count our spectral categories, we can say just count medium and strong vegetation or something like that, and make maybe a ratio to the total amount of valid observations. It's maybe a bit more clear from this slide. So that is an aggregation for 1 year in Austria, where we map the pixel, how often vegetation has been seen in valid observations. So snow and cloud-covered pixels are removed. So if we have one stack where we have 50% cloud cover and 50% is vegetation, then it gets a label of 100% vegetation in all valid observations. This can now be transferred to all other years. It's parameter-free and cloud snow cover independent. And we use really every pixel we have from Sentinel-2 in this field. And now we come to the layer and the idea here. We are not the first ones who are doing an RGB compositing, but I explain in the next slides why it's a bit different and why we have in the title, it's still easy to interpret here. So we use now the RGB color model to visualize the vegetation status of different years. For example, time 1 would be 2018, time 2, 2021, time 3, 2024. The oldest we put on the red channel, middle one green, and the newest on the blue channel. And then we get such a composite which can interpret it with the following cube. That is now not a data cube, it's just a visualization cube. Don't mix that up. You see T1 red color, T2 green color, T3 blue color. And the colors have then the following meaning. So red color means vegetation in T1, yes, but no vegetation in time 2 and 3. Yellow means vegetation loss in the last step. Blue, for example, vegetation gain. Magenta, vegetation gain, but there was vegetation loss in between. And then, and if I show the example, that's important, white and pastel colors mean always more or less a lot vegetation. That can vary a bit. We have different types of data below that, and also different types of how cloudy a year was. And black means we have never seen vegetation. So, okay, sorry, I speed up a bit. So here again, that is a gravel extraction site near Linz in Austria. You see how that develops over time. Blue means it's already regreened. Below you see the newest Sentinel-2 image of that area. It's again regreened, but we know for the blue one, it was not vegetated in the years 2021, 2018. Red means it has a loss of vegetation since 2021. Yellow, a loss since 2024. Then we see also this greenish part in the upper part, that's a typical agricultural area. And if you see into the table, we can still, because we encode that in percentage, in integer values, we can still see for the yellow color, for example, for that cross I marked here, 100% color for 2018. So all valid observations in that year were vegetated. And for the agricultural area, we see, okay, 50%, so 50% bare soil, 50% vegetation, typical behavior for that. That we mean by that we can still interpret these composite. And that's a big difference if you, for example, make a composite of different NDVI results. You first don't know, NDVI is not only positive for vegetation, but you don't know really how much was there vegetation per year. You have only an indication, and here we have counted numbers. That's now just a short video of the implementation for Austria. We are doing that for every year. That is now a combination, again, 2018, 2021, 2024. like it's implemented also now in GTIF Austria, so you can look that up on the web. We have different outputs there, slider map to compare. You can compare it with Sentinel-2 data and so on. What you see here is now a reservoir in the Tyrolean Alps where they built that in different stages. You see in red, older vegetation loss, yellow, newer vegetation loss. So different application areas. If you go, for example, into forested areas, we have big bark beetle problems after storm events in the last years in Austria. You can see that here. You can also see some regreening parts and different loss of vegetation. If you go into a city like here, Graz, you see the black part that is built up for all the times, but you see also new construction sites, new streets, which are very colorful. When we now fly to, these are now the gravel extraction sites. You have already seen where it's very prominent how that behaves, how that is regreened, how that is re-established again. If you now fly in the direction of Vienna, you see agricultural areas are very colorful. We have always different crop types that influences how often that is vegetated. But if you know as a domain expert where is agricultural area, where is forest, you can overlay that and you can focus on these areas and see the changes. You see the Danube River always not vegetated, which is like here. Okay, next part would be then Vienna, some construction sites. I think that explains it. You can look up that video also online, so I will skip to the next slide to speed up a bit. So that's now implemented in the GTIF AT, so Austria, subset of the initial GTIF initiative. We will extend that to all years since 2015. We know bit problems for 15 and 16 where we have only one Sentinel-2 satellite, but it still works quite well. We designed that to improve the communication of multi-temporal analysis to a broad range of users. So we are in contact in this project, in which we are developing that, with authorities, decision makers, non-EO experts from different domains. And we think it's particularly effective to use it as a WMS or whatever base map in a GIS. So you know that base maps are nice, but you never know what is the date of that image, what is the date of that, and here we have a multi-temporal analysis. And since it's seamlessly combined with our semantic Earth observation data cube, you can also, on the fly for smaller areas, create your own combination of different years or half of years, whatever you prefer as a user. Yes, and the potential application areas, I showed some of them. Green space, their dynamics, land use changes, soil sealing. In Austria, a lot of vegetation change due to energy production, so wind turbines, solar things, forest monitoring, and so on. There are some links where you can look that up. It's all public. The layer is free. All years will be free if they are published. We are also thankful for getting sponsored by the Austrian Research Promotion Agency in 2 projects who implemented that. Thank you very much.
Thank you very much, Dirk. Impressive. Do we have questions from the audience for Dirk? If there are no questions, then I have some questions to you, Dirk. There were on the conference some talks about different sort of movements towards ZAR, GDDS, etc. So what did you use underneath, and what are you planning for the future in terms of evolutions? How do you see that in your case?
In our case, we are a small research group. The Semantic Earth Observation Data Cube, we prototype for Austria. We have all data in there. For us, it's hard enough to have all the infrastructure there, but we have some demo cubes for other areas of the world, Syria, Afghanistan, so demonstrate that it's transferable. And we, in the last years, with ESA and Cube money, we automated the semantic enrichment so that we can do that worldwide. So everyone is invited to ask for that in the ESA NOR, Network of Resources. So our aim is to show that it works, make it scalable. We are maybe not the ones who can scale that for the whole globe. We have not the infrastructure, but we try to do the research to make it scalable.
Thank you very much, Dirk.
Thank you.
So we move to the last speaker of this session. Next speaker is Nini Nian Lin, also from University of Salzburg, and she's going to speak about from cloud to client web native in-browser EO data cube exploration and analytics using ZAR. Oh, sorry.
Okay. Can I start? Yeah. Hello, everyone. I can sense that everyone is tired and we are a little bit late on the schedule. So if you don't mind, I will go through my presentation a little bit quick and simplify. Right? So today I'm going to present how we implemented web native in-browser EO analytic data cube exploration and analytic implementation fully in the web browser. Right? So this development work comes from the SpongeCity Interact project. So I will start with this background context. So the SpongeCity is an Interact project that tries to tackle climate change effects in the urban environments in Danube region projects, in Danube region cities. So our role in this project is to develop an observation data-powered toolbox that helps the cities assess risks and plan SpongeCity measures across the city. Right? So this toolbox is meant for a broader public and people in the municipalities, local communities, and stakeholders. So the important thing is that this toolbox has to be accessible and also simple. So in formulating this toolbox, we begin with the 3 given requirements first. So the first important thing is that this toolbox has to be sustainable and transferable after the project period has finished. Right? So this toolbox, this dashboard, has to be alive. So we need to reduce a lot of system complexity and the back-end infrastructures for this. And on the other hand, this toolbox must support interactive data exploration and perform the analysis functions in one environment. And the next requirement is that this toolbox has to be ran on the standard laptops or tablets, and no software installation required because of the target audience of our toolbox. So these are our requirements and constraints. So we try to find a solution that might fit the problem. So after some research and experimentations and prototyping, we came up with a solution architecture. So the solution is that we are going to use the ZAR data format, and we are going to do all these analytics and visualization entirely in the web browser. So is it possible? We prototype and tested it, and it's very possible and feasible these days, especially with the latest web technologies available. So I assume we already have an understanding of the ZAR, but why we chose ZAR? The whole idea is that it is cloud native, and we can read subsets, so temporal subset or spatial subsets of the data sets through the interface. Right, so this is the ZAR structure that we use. We have hierarchical zoom levels for the map visualization purpose, and each zoom level groups have time, space, coordinates, so that we can calculate the indices of the data chunks to retrieve from the client side. And we pre-calculate the statistics and keep it as a separate array for each timestamp. Like this is useful when we visualize the map, the column maps and scales and everything, so that the client side doesn't have to do the statistic calculation again. Right? And the values are stored in time band Y and X format array. So this is the whole system architecture. Right? We store all the EO data sets as a ZAR data cube, and we put them in the main IO object storage. It can be Amazon S3 or whatever. Right, and on the client side, we use the Zarita.js, or you can use Zar.js to retrieve the ZAR data chunks from the object storage. Right, and we have 2 paths here, one for the visualization and one for the analytics. So in the visualization part, we adopted open layers, and we developed an extension called Open Layer ZAR that use the ZAR data chunks and visualize map directly in the open layers map. And on the other hand, for the analytics, right, we retrieve the data chunks using the Zarita.js, and we pass this data into the web worker thread so that it doesn't block the main UI. But from there, depending on how complex or performance greedy your analysis functions are, you can choose to use Vanilla.js or WebAssembly or WebGPU or even if you want to run machine learning, deep learning, lightweight models, you can use ONNX frameworks to do that. Right? So in the end, after processing, the results are delivered right back into the map and the other chart visualizations layer. So to test this implementation, we implemented 4 test analysis functions, and we tested this in the Pesh municipality, which is one of our pilot cities in the project. And we ran these tests in 2 data sets, 70-meter resolution and 10-meter spatial resolution data sets. Right? And you can see the performance. And you can find that most of them, the analysis are finished within a few seconds or a few minutes on the laptop and the iPad. Right? We have 2 separate setups. So, now I'm going to show you the demonstration of this interface, how fast it is, so that you can see by yourself. But if you want to test it out on your laptop or on your tablet, you can go to this website and experiment yourself. Okay, so this video, how can I? Okay. So this demonstration shows how the SAR data layers are visualized in the web interface, right? So this is really quick. You can zoom in, zoom out, pan around, right? So it's like the same interaction that you can receive from the web map service server or tile services like that. But this, we are reading data directly from the data set, from the source of the data. There's no tiling servers existing in the backend. So, and here is a demonstration of urban heat island analysis that we implemented. So it's the same concept. We are reading directly from the data set in the object storage, and we analyze the data. And so here we set a temporal period, and we define the spatial period. And the backend, the web workers calculate the indices of the data to load, and the data is retrieved from the object storage, and the calculation happens in the background. Okay, so when we start the analysis and it retrieves the data, do the processing, then it's done. So this video is real time. It's not sped up. So, and you can also see these statistics calculated in just that split second. Okay, the next video is a similar demonstration. This is occurrence threshold analysis on the greenness index data. But the point here is that this is the meter resolution data set for the same spatial area. Right? So it's now retrieving the data set. Then now the computation is doing. It's finished. So it's all happening in your web browser, in your laptop. There's no backend infrastructure, only the object storage needed. Okay, so as you can see, it's very feasible to implement this, and it's also responsive in real life use case. Right, but there's some limitations and the challenges that we have to address. Right, so one of the most important thing here is that because the JavaScript community is not as strong as the Python or the Julia or our communities, we don't have a lot of geospatial, especially with the grid data processing libraries or frameworks in the back. Right, so the demonstration that I did here only implied 1 data set. Or even if you want to use 2 data sets, it has to be harmonized, spatial resolution, X10 or CRS, right? So there's this challenge that we still have some barriers to go through. But technically, it's very possible to move into the client side, into the browser, right? Not only doing things in the backend, in the Python, in the server side, right? Okay, so the conclusion, so as you can see here, this implementation can work really well with the Cityscape Earth observation data sets and with the targeted analytics implemented directly in the web browser, right? So the exact implementation of these analytics depend on your use case. Like we cannot download all every possible solutions, right, that fits all for every possible cases, right? So we can implement the targeted analytics for our specific cases, right? And yeah, so what's next? Like I said, we have data harmonization problems with the spatial projections and things. So the discrete global grid system could be a solution to this. And also we can look into the web GPU acceleration or web assembly accelerations further. So I would like to acknowledge my team. Thank you for your contributions. And if you want to reach out to us for collaborations or have any discussions that you want to go, please contact us. And thank you very much.
Thank you. Are there any questions in the audience? There's one over here. Can we have a microphone? Thank you.
Thank you. Thanks a lot. Impressive work. So you mentioned it is designed for specialized analysis, but how do you see it feasible to make it generic, like supporting a raster calculator or something similar so that people can use it for arbitrary analysis, and also for different data formats, so including ZAR, but maybe COG and similar. So that's my first question. The second one, there are also some initiatives like Jupyter GIS, which also brings GIS capabilities to web browser. And it looks like your work can be really quite complementary to bring some computation capabilities. So are you in collaboration with them, or how do you see this possibility? Thank you.
Okay, thank you. So for the first question, the way I see is that the barriers we have for this generic broader framework is that the first thing is we don't yet have a standard, like we have GeoZar conventions going on right now, but so there's no established standards or the conventions frameworks that we have, right? So it limits the implementation of interoperability and these, right? So for example, the demonstration that I show here is that we are hosting our own data set, data cubes, right? But in the future, it can happen that you host your own data set, but in a standard way, right? Compliant. So like, the idea is like you don't have to host your own data set. You can just pull data from any of the other servers and do analysis in your web browser, right? But another barrier is that, like I said, the community, especially the community, the developer community for the JavaScript implementation is not as strong as so to create this generic support for all possible analysis, right? So it takes a lot of effort and contribution, right? So we need interest and a community to try to push into this direction, right? Because I understand JavaScript is not really a good thing to do these kind of things, but there are some use cases and niche cases that can try to solve some problems, right? So the second question, sorry, can you ask the question again for the second one?
The question was, there are initiatives like Jupyter GIS, which brings GIS capabilities to web browsers. So how is your collaboration with them, or are you planning something like that?
Thank you. So technically, I have no connection with them. Right, so the way I see is that my approach is most focused on the front end implementation JavaScript side, right? So I try to forget and abstract any possible backend support systems. And so if maybe there's a Jupyter JavaScript developments happening, right? But it still relies on the Jupyter backend system. I assume. I assume. So and also, so what I wanted to demonstrate here is that you can implement these analysis functionalities by yourself, right? Without, like, I didn't use any other software libraries except for the jari.js, right, to retrieve the data set. But you can implement your own analysis functions with this pipeline structure, right? So as you can see, it's really efficient with this modern performance. So I'm focusing in that.
Great. Thanks again. I think we'll close here. Thanks again.
Okay. Thank you.
And thanks everyone for attending the session. Just a reminder that the demos are going on downstairs in the basement area now. Also the booths worth visiting, and the Birds of the Feather event is going on. So a lot of things to check out now. And then we hope to see you later at the dinner, 7 o'clock at the BiDS conference dinner. Thank you.